Hey everyone, let's continue talking about power series. So what I have at the top of the page here is just the general form for a power series like we had in class. A sub n in this case is kind of giving you just a formula. So this part looks like a regular series formula. And then the C value is filled in with some number, and that number is the center of the power series. What we'll talk in this video is actually going to show you why it's called the center. So usually this is an actual x right here. So you'll have x minus 5 raised to the n, or x minus 1 raised to the n, where that x minus the same number is in every term as you spell it out. So this x in the power series is an actual x. So when you actually compute out the first few terms of a power series, it sort of looks like a series because you're adding a bunch of things up forever, but every term, instead of just being a number, actually has an x in it as well. So it's sort of like a function that you can plug x into. So what we'll talk about in this video is the interval of convergence, and you can see the formal definition already on the page here. Feel free to pause this video at any point so that you can write stuff down. So the interval of convergence of a power series is the interval of all x values for which the series converges. Okay, so this is what we'll actually be doing with power series for the most part. So you'll be given the formula of a power series and asked to find the interval of convergence. Now, one thing to notice is when we say interval, this is actually going to be an interval notation. So, something like 0 to 10 with like brackets and parentheses, that kind of thing. So you're going to write these in interval notation. And it's going to be the set of all the x values that make it a convergent series. So the first one that we're actually going to talk about is one that we saw in class, just the series n equals 1 to infinity of x to the n. And if you spell it out, that's 1 plus x squared plus x cubed, and so on. Now, I want you to notice, we're starting with this particular series because we actually know a lot about series that are formed this way. So let's say x equals 2. You would have the series 2 to the n, 1 plus 2 plus 4 plus 8, and so on. Or if you have x equals 2/3, you would have 2/3 to the n. All I'm doing is plugging these numbers in for the x value up there. And this would be 1 plus 2/3 plus 4/9, etc. Now, what's happening when we actually plug numbers in is that we're seeing geometric series. And we know the rules for geometric series. So no matter what we plug in for x, the a value is 1, and the r value for the geometric series is whatever you choose for x. X can be a positive number, a negative number, a fraction. Whatever you choose for x would be the r for the geometric series. And we know that a geometric series converges if the absolute value of r is less than 1. Oops, now it's on the screen, that'd be helpful. So we know that a geometric series converges if the absolute value of r is greater than 1, and it diverges otherwise, right? And the r in this particular setup is the x from the series. So my interval of convergence will be the interval that is all the numbers whose absolute value is less than 1. If your absolute value is less than 1, then you are stuck between -1 and 1. So my interval of convergence is the interval -1 to 1, and I'm using parentheses on both edges because neither -1 nor 1 are included in this interval. They're both in the divergent category. So for this particular one, it's just strictly between -1 and 1. So for every other power series that we're given, the answer won't be quite this cute, but this is a nice way to start because it's one where we already know the rules, so we can skip the steps and just kind of see what the interval of convergence actually means. Now, another thing you may be asked to compute is called the radius of convergence. So we'll make this a definition, but it'll be fairly informal. The radius of convergence is always going to be half the length of the interval of convergence. So notice -1 to 1. Let's think about it on a number line just for kind of a visual here. So I have 0, -1, 1. So my interval of convergence goes from here to here. See how 0 is smack in the center of that interval? Like it's literally at the halfway point. That's why it's called the center of the power series. So if we go back to the original power series, this is x minus 0 to the n. So the center here was 0, the c from the power series formula. The center is always literally in the middle of your interval of convergence. That's why it's called that word. Now, the radius of convergence is going to be how far from the center you can get. So it's always half the total length of the interval. So you can get as far as 1 away from 0 here. The length of this interval is 2, so the radius is 1. So if we were also asked for the radius of convergence, we would have said 1. Usually when you're asked for the interval of convergence, they'll also ask for the radius just because it comes for free with the answer. Now, if we had brackets on either one of these edges or both, my radius would still be that 1. The radius doesn't really care about whether it's brackets or parentheses at the edge. Okay, so like I said, when we're doing a general interval of convergence problem, we're not going to be able to just jump straight to a rule. So let's talk about a general strategy that will work every time. So this is our general strategy for interval of convergence. Okay, so what you're going to use is the ratio test. And this can be done with things like the root test, but we're going to just stick with the ratio test because honestly, it's the best one. All right, so you are going to put your power series into the ratio test, but it's going to be the version that has the absolute value. We need the absolute value because depending on the value of x, our terms might be negative or positive or a little bit of both. So if we can show that this limit comes out less than 1 with the absolute values, then we're showing absolute convergence. So what you'll get here is the x values that give you absolute convergence. And then the x is kind of at the edges. So in this case, like the -1 and 1. The ones at the edges will be like the inconclusive case here, and you'll have to check them individually. And I'm going to jump right into an example to show you what I mean there, because this takes a lot of work from here to here. Okay, so we're going to jump into our example series here to see how kind of an average typical interval of convergence problem will go. So we're being asked to find the interval of convergence and the radius of convergence of the series from k equals 1 to infinity. So in this one, I'm using a k instead of n. It makes literally no difference. It's just switch all your n's to k's in the formulas. And then we'll have 1 over k x minus 3 to the k power. Okay, so notice a couple of things here. So for 1, my center, the c value, is 3. So I'm expecting my interval of convergence to be something that's like symmetrical around 3, right? So it'll be, 2 in either direction or 1 in either direction, whatever the radius is. Also notice that this power series is the first one we've seen that starts the index at 1. That's totally fine for a power series. It's no big deal. And really this one's starting at 1 because you can't plug 0 into this formula here. Okay, so we are going to follow the strategy that we just listed, which is jump straight into the ratio test with the absolute values in it. So we'll have k go to infinity because k is my letter. And I want the absolute value of am plus 1 over, oops, k plus 1 over ak. Okay, so the k plus 1 term is 1 over k plus 1, x minus 3 to the k plus 1. And then the k term is just exactly what I see there. So I'll have 1 over k, x minus 3 to the k. Now, there are lots of options here for how you simplify it, what you do in what order. It's really flexible, so kind of just go with what your preferences are. For example, the absolute values, they really only need to be on this stuff, because this is the stuff that might be negative. We know that k plus 1 and k are definitely positive. So you can move your absolute values around or wait until the end. Another thing you can do is write it as fractions. So feel free to try your way and then check it and see if it matches my final answer. So to try to simplify this, what I'll do is think of this top as x minus 3 to the stuff over k plus 1. X minus 3 to the k plus 1 over k plus 1. That's my numerator. I just kind of put this as the top of the fraction. And then same thing here. If I have x minus 3 to the k as this numerator, and then I do the times the reciprocal, I get that. Okay, so the k and the k plus 1, it seems like they should interact. But really they can't, I mean they interact, but they can't cancel with each other, right? Because it's a k here and a k plus 1 there. With this addition, it kind of stops you from canceling anything. But the x minus 3's definitely can cancel. So whatever k is, you have x minus 3 times itself a bunch of times on the bottom. And then on the top, you have the same thing, x minus 3 times itself a bunch of times. And it's one more time than the one on the bottom. So this is like to the 11, and this is to the 10, or this is to the 21, and this is to the 20. They'll all cancel except for one on the top that didn't have a buddy. So this cancels to just an x minus 3. And we can put it on the top, or we can kind of put it on the side so that the k over k plus 1 we can consider separately. Again, lots of flexibility for how you compute this. Now here's the crazy part. We have k's and we have an x. K is the thing going to infinity, and x is just a mystery number. So the limit is really only happening here. So as k approaches infinity, k over k plus 1 goes to 1. You can do the leading terms trick, you can do L'Hopital's rule, but this comes out to 1. And it's just 1 times whatever x minus 3 is in absolute value. So my actual answer for the limit itself, my like capital L, is the absolute value of x minus 3. And it's really times this 1 that I'm not writing because I don't need it. And this is weird, but it actually kind of makes sense if you think about it in the right way. So what having an x in our answer here means is that this limit depends on the value of x. Depending on x, it might be less than 1 and you'll get convergent, or it might be greater than 1 and you'll get divergent. Which actually makes complete sense because x is going to change the series itself. So we can tell that this converges, my original series slash the absolute value version of it, converges if my value of L, so absolute value of x minus 3 is less than 1. It diverges if I am greater than 1. And then the equals 1 case is inconclusive. Okay, so what I have here is the beginnings of my interval of convergence. So we want all the x values that make it converge, and we know that if the absolute value of x minus 3 is less than 1, it's convergent. Now, if the absolute value of something is less than 1, it's trapped between minus 1 and 1. And if I had the absolute value of whatever less than 5, I would say, oh, well, the stuff in the absolute value is between minus 5 and 5. Now, what I'm going to do is add 3 to all 3 pieces. because I'm solving for x in the middle. And I get 2 is less than x is less than 4. I'm inching really close to my answer for interval of convergence. So my interval, the x values that make this converge, is 2 to 4. All that's left to decide is if 2 or 4 is included in the interval, because if x is 2 or 4, you fall into the inconclusive situation and the ratio test just doesn't know. So that's why we said in the strategy, we have to check those endpoints individually. That's what's happening here. So we still need to check x equals 2 and x equals 4 separately. And they're just kind of like single special cases to see. So notice if we only needed the radius of convergence, I could stop here and say my radius is 1, right? Because 3 is in the center, which makes complete sense because our center is 3. So you can get up 1 or down 1 from 3. So my radius, let me actually just write that down now. My radius of convergence is definitely 1. The interval, we've got to get more specific. Okay, so we're going to check x equals 2 and x equals 4. And all I'm going to do for x equals 2 is just come back to my original power series and put a 2 in for x right here. So I have 2 minus 3 is negative 1. So I have the series from k equals 1 to infinity, 1 over k, and then 2 minus 3 was negative 1 to the k power. Now I need to decide if this plain old classic series is convergent or divergent. I encourage you to pause this video and decide for yourself. What you should get is that this is convergent by the alternating series test. This is an alternating series with the negative 1 to the k. The 1 over k's go to 0, so it passes the alternating series test with flying colors. So that means that 2 is in my interval of convergence. Okay, so now we're going to do something very similar for 4. We'll come back up to the original power series and put a 4 in for x here. 4 minus 3 is 1. So I get the series from k equals 1 to infinity, 1 over k times positive 1 to the k power. And that subtle change makes all the difference. 1 to the k power is always 1. So I can actually just drop it entirely, and what I'm left with is our old friend, the harmonic series. And the harmonic series diverges. Let's say by the p-test, even though we know this particular series really, really well. Let's say it's specifically because of the p-test. So that means that 4 is not in the interval of convergence because 4 did not make a convergent series. There we go, so 4 is not in the interval. Okay, so we're gonna say the interval from 2 to 4, including 2, but not including 4. So my interval of convergence here will be bracket 2 to 4, and then a parenthesis on the 4. And we already said the radius of convergence is 1, which agrees with that there. Okay, so this video is already getting really long, but I just wanna just rewind to the top and recap what just happened, because the steps here are a lot, but you'll always take the same 2 steps. So to find your interval of convergence, you're going to jump into the ratio test with absolute values, compute, 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 and what you'll most likely get is something that depends on x. So you say, okay, well, if that thing is less than 1, then I'm convergent, and you want to kind of solve that into an inequality. You'll have kind of 2 edge points. A great way to double check your final answer is to make sure your center really is the center of your interval. Then you'll take those 2 edges that you get and check them individually, decide convergent, divergent. That'll change every time. And that'll tell you to use brackets or parentheses. And then your final interval of convergence will combine all of those things. The radius will be half the length of that interval.